We will solve the exercises acid-base according to the parts recorded. We started by part 1, notation. Exercise 1, which of the following statements are correct? So we have A, B, C, D, and E. A, based on Bronsted, an acid is a species likely to donate a proton. So A is true according to the definition of Bronsted. An acid is a substance that releases HCO+. A base is a substance that accepts HCO+. A strong acid has a weak conjugate base. This is false since our study in solution, in chemistry of solution, is in aqueous solution where we used water as solvent. And as we said, the pKa of the couples are between 0 and 14, and for each couple, the acid is weak and the base is weak. So according to this increasing order of pKa, as pKa increase, the strength of the base increase, and as pKa decrease, the strength of the acid increase. So OH- is the strongest base, and HCO+ is the strongest acid. So B is false. A strong acid has a weak conjugate base. We can correct. A weak acid has a weak conjugate base in solution. C is false. D is true. A weak base has a weak conjugate acid for any couple of pKa between 0 and 14. E is false. So the correct answers are A and D. As to exercise 3, what is the correct pH definition of an aqueous solution? We know that pH equal minus log HCO+, so the correct answer is B. Exercise 4, the correct definition of the acidity constant Ka of an acid-base couple is, we know that the HA dissociate in water to give A- and HCO+ till the equilibrium. So at equilibrium, K equal Ka equal concentration of A- at equilibrium times HCO+ at equilibrium divided by HA. To note that Ka is an identity of the couple HA A-. So the correct answer is B. Exercise 5, the pKa of acid-base couple is defined by, we know that according to the definition of P function, P is potential, the potential of X is equal minus log X. So pKa equal minus log Ka, and the correct answer is D. We pass to the second part concerning the strong acid and the strong base. Exercise 8, if a strong acid is diluted 10 times, what would happen to the pH? Decrease by 1 unit, remains the same, increase less than 1 unit, or decrease less than 1 unit, or increase by 1 unit. So the objective of this exercise is to calculate the pH of strong acid before and after dilution. And the conclusion is the dilution did not affect the dissociation of strong acid. A strong acid always dissociates completely to HCO+. So we have dilution 10 times C initial, V initial equal C final, V final, and the factor of dilution equal 10. So C final equals C initial divided by 10. What is the formula of the pH that can be applied? The formula of the pH that can be applied is pH equal minus log C final, since the acid is strong and it has complete dissociation to HCO+. HCO+ in solution after dilution equal the final concentration, which is equal to the initial concentration of the strong acid divided by 10, and the initial concentration of the strong acid is equal to the initial concentration of HCO+. So pH equal minus log C final equal minus log C initial divided by 10 equal minus log Ci minus log 10, so minus log Ci plus log 10, so the pH equal pH final is equal to pH initial plus 1. So the correct answer is E. We pass to exercise 23. What is the pH value of hydrochloric acid solution of concentration 10-8 mmol per liter? The objective from this exercise is to know which formula should be applied according to the domain of the concentration. If the student write that hydrochloric acid is a strong acid, so he will apply directly pH equal minus log C. So pH equal minus 10 to the power minus 8. So pH equal 8, and this is a basic medium. It's impossible that hydrochloric acid form a basic medium. And we explained in the course that we have 3 domains of validity for the strong acid. If minus log C is greater than 8, pH equals 7. If minus log C is less 6.5, pH equal minus log C. And between 6.5 and 8, we have to apply the second degree equation. Or according to the concentration, we define the 2 domains 10-8 and 3.2 10-7. So if the concentration is less or equal 10-8, pH equals 7, and this is the case in this exercise, the concentration equal 10-8 molar, which is in the domain of pH equal 7. So the correct answer is C. Exercise 24. Assume that for the given concentrations, the standard hypotheses are valid. Calculate the pH of a solution obtained by dissolving 0.12 of sodium hydroxide NaOH in 500 milliliter water. We know that sodium hydroxide is a base. And since no Kb or Ka value given, so NaOH is a strong base. And in the strong base, we have 3 formulas according to the domain of validities. And these formulas depend on the concentration of the base. So first of all, we have to calculate the concentration of sodium hydroxide solution. The concentration is equal to the number of mole solute divided by the volume of the solution, and the volume of the solution is 500 milliliter, because we suppose that the addition of 0.12 grams of sodium hydroxide did not change the total volume. So V equal 500 ml in liter equals 0.5 liter. So the concentration equal the mass 0.12 divided by the molar mass of sodium hydroxide is 40 gram per mole times the volume of the solution 0.1. So the concentration of sodium hydroxide solution is 6 10 minus 3 molar. NaOH is a strong base, and the concentration 6 10 minus 3 is greater or equal 3.2 10 minus 7. So we apply directly the formula pH equal 14 plus log C equal 11.78. So it's equal approximately 11.8. The correct answer is D. Exercise 25. Consider a solution of potassium hydroxide, which is a base, of 0.05 mole per liter concentration. The following dilution is carried out. 10 milliliter of this solution, so 10 milliliter of concentration 0.05, are placed in 500 flask, and distilled water is added till the mark. Which of the following statements are correct concerning the obtained solution? So in this exercise, we have dilution of the initial concentration of sodium hydroxide. And the dilution law, C initial, V initial, is equal to C final, V final. So the C final equal C initial, V initial divided by V final equal 0.05 times 10, which is the initial volume, divided by V total, because in the exercise we add water till the mark, so till 500 milliliter. So the concentration after dilution is equal 0.001 molar or 10 minus 3 molar. So A, the concentration of the OH minus is 10 minus 3 mole per liter. A is correct. The concentration of HCO plus is 10 minus 3 mole per liter. This is false, since OH minus concentration times HCO plus concentration equal Kw. The formula pH equal pKw plus log C can be applied, where C is the concentration of potassium hydroxide in solution. KOH is a strong base, and the concentration is greater than 3.2 10 minus 7 molar. So the formula applied is pH plus log equal pH equal pKw plus log C. So the pH equal 14 plus log 10 minus 3, so 14 minus 3 equal 11. So C is correct. We have till now two answers correct, A and C. We pass to D. The pH of the solution equal 12.7. This is incorrect. We calculated the pH equal 11. So D is false. And E, the pH of the solution equal 11. This is true. So the correct answers are A, C, and E. We pass to part 3 concerning the weak acid and the weak base. Exercise 6, the pKa of the couple acetic acid acetate is 4.8. For an acetic acid solution in water, we can say the acid completely dissociate into its conjugate base. This is false, since the weak acid dissociate partially, so we have weak dissociation. Part B, the dilution favors the dissociation. This is true. Dilution of a weak acid increase the strength of this acid, so it will increase the dissociation. In part C, if we dissolve 0.1 mole of acetic acid in 1 liter of water, at equilibrium, half of the acid is dissociated. So alpha equals 0.5 in part C. So we have to calculate the real value of alpha. We consider the equilibrium of acetic acid in water to acetate and HCO plus at T equals 0. The concentration C 0, 0. So C minus X, X, and HCO plus X. And X equal alpha times C. So at the equilibrium, we have concentration C 1 minus alpha for acetate, alpha C, and for HCO plus alpha C. Ka equal acetate at equilibrium, HCO plus at equilibrium, divided by the acetic acid, so equal AC, alpha C times alpha C, divided by C1 minus alpha, so equal C alpha square divided by 1 minus alpha. So C alpha square plus Ka alpha minus Ka equal 0. And according to this quadratic equation, we will find a relation between C and alpha, and you will observe as C decrease, so in case of dilution, alpha increase. This is the answer of part B. Now, what is the value of alpha? You solve this quadratic equation, the concentration equal 0.1 divided by 1, so 0.1 molar, alpha square plus 10 minus 4.8 alpha minus Ka minus 10 minus 4.8 equals 0. You will find the acceptable value of alpha equal 0.0125, or percent alpha equal 125%. What is the meaning of this value of alpha? So this value means that only 1.25% of acetic acid dissociate. So C is false, because in C they supposed alpha equal 0.5. In part D, acetate is a strong base. This is incorrect. Acetate is a weak base, since pKa value of this couple is between 0 and 14. In part E, we have to calculate the pH, and the pH proposed is 4.8. So what is the pH of our solution? pH of the solution equal minus log concentration HCO plus at equilibrium, so equal minus log alpha C. HCO plus equal alpha C, C equals 0.1 times 0.0125 calculated of alpha, so the concentration of HCO plus at equilibrium equal 1.25 10 minus 3. pH equal minus log HCO plus, and you will obtain a value 2.9, so E is false. The correct answer is B. We pass to exercise 7. Given the following couples with given pKa, which of the following statements are correct? The objective of this exercise is to know how to classify the couples according to pKa scale and to compare the strengths of acids, weak, and the strengths of weak bases. So first of all, we have to classify all couples on increasing order scale of pKa. pKa scale, we have the couple we put on the left side, we put the base, and on the right, we put the acid. So we have NH3, NH4 plus, acetate, acetic acid, and we have Cl, CH2, CO minus, and Cl, CH2, COOH. As explained before, any couple of pKa between 0 and 14, the acid of the couple is weak and the base of the couple is weak. As pKa increase, the strengths of the base increase. As pKa decrease, the strengths of the acid increase. OH minus is the strongest base in solution, and HCO plus is the strongest acid. So now we return to analyze the statements. A, NH3 is a weak acid. This is false, since ammonia is a weak base. With equal concentration in water, acetic acid dissociates more than the ammonium. So he proposed that acetic acid is a stronger acid than ammonium. And this is true, since pKa of acetic acid is less than pKa of ammonium, or in other words, Ka of acetic acid is greater than Ka of ammonium. So statement B is true. C, Cl, CH2, COH is the strongest acid among the above species. Since Cl, CH2, COH has the lowest value of pKa, that means this weak acid is the strongest between the others. So C is true. D, ClCH2 COO minus is the strongest base among the above species. ClCH2 CO minus has the lowest pKa. So it's the weakest base. So D is false. In part E, CH3COO minus is the weakest base among the above species, and this is also false because the weakest base is ClCH2COO minus. So the correct answers are B and C. Exercise 15. Consider 1 liter of acetic acid solution, 0.1 mole per liter. Question A, calculate the degree of dissociation alpha. Since acetic acid is a weak acid, it will dissociate partially to acetate and HCO plus till the equilibrium at T equals 0, C 0, 0. At the equilibrium C 1 minus alpha, C alpha, C alpha. So Ka equal the concentration of the product divided by the reactant at equilibrium. So equal C alpha times C alpha divided by C 1 minus alpha so equal C alpha squared divided by 1 minus alpha. So alpha squared divided by 1 minus alpha equal Ka over C equal 10 minus 4.8 divided by the concentration is 0.1 divided by 1, 0.1 molar. So alpha squared divided by 1 minus alpha equal 10 minus 3.8. We have to solve the second degree equation, and we will find that alpha equals 0.01258. We pass to part B. What volume of water should be added for alpha to be multiplied by 2? What is the meaning of adding water? When we add water, we make dilution, and dilution will increase the dissociation of the weak acid, so alpha will increase. The question is, what dilution factor should be done, or what is the volume of water added in order to have a new alpha which is equal to times initial alpha before dilution? So if alpha is doubled, I will name it alpha second. So alpha second equal to alpha, so equal 0.02516. We rewrite the equilibrium of dissociation of acetic acid, and we have the same value of Ka before and after addition of water, since Ka is an equilibrium constant that depends only on the temperature. So Ka is the same, equal C second alpha second times C second alpha second divided by C second 1 minus alpha second. So C second equal Ka 1 minus alpha second divided by alpha second square. You put the values, and you obtain concentration equal 0.02441 molar. To note, the initial concentration was equal to 0.1. We add a certain volume of water, so the final concentration, C second, is 0.02441, so the concentration decrease, and this is a dilution. The question is to calculate the volume of the water added. The dilution law, C initial, V initial equal C final, V final. C initial equal 0.1, V initial equal 1 liter, C final is equal to C second equal 0.02441, and V final, the final volume, is equal to the V initial, which is 1 liter, plus the volume of the water added. So you do the calculation, and you will find that the volume of the water added is equal to 3.2 liter. In this expression, you have to correct C initial, V initial equals C final, V final. Calculate now the pH of the obtained solution. The pH of the obtained solution is the pH of the diluted solution. And the diluted solution is a weak acid. So we have to know what is the formula that should be used. We compare the concentration C second to the value of Ka. We find that C second is greater or equal 100 times Ka, so the formula of the weak acid that can be applied equal half pKa plus Pc, or half pKa minus half log C, Or you can apply simply the pH equal minus log HCO plus in the solution equal minus log C second alpha second, and you will obtain a pH equal 3.2. Exercise 16, calculate the dissociation Ka, dissociation constant Ka of weak acid HA. We know the percent ionization 60%, and alpha is equal 0.016, and the concentration of the solution equals 0.0950 molar. So we have to write the dissociation of the weak acid in water. At T equals 0, we have C0, 0, 0. At the equilibrium, C0, 1 minus alpha, C0 alpha, and C0 alpha. So Ka equal A minus HCO plus divided by HA equals C alpha squared divided by 1 minus alpha. We put the value of alpha 0.016 and the concentration equal 0.095 divided by 1 minus 0.016, so it's equal to 2.47 10 minus 5. So the correct answer is E. To note that the dissociation of this weak acid is 60%, and alpha exercise 16, calculate the dissociation constant Ka of a weak acid HA. The percent ionization is 1.6% or alpha equals 0.016 in a solution of concentration 0.0950 molar. So in this exercise, we have to write the dissociation of the weak acid in water. HA dissociate in water to HCO plus and A minus. C0, 0, 0, the concentrations at equals 0. At equilibrium, C0, 1 minus alpha, C0 alpha, C0 alpha. So we write Ka equal A minus HCO plus HA concentration at equilibrium. So it's equal to C0 alpha squared divided by 1 minus alpha. We put the value of C and alpha, and we obtain a Ka equal 2.47 10 minus 5. To note that this acid used is weak, of weak behavior, since alpha is equal 1.6% less than 20%. So the correct answer is E. Exercise 17. An acid HA is placed in water solution with a molar concentration of solute equal 10 minus 3 molar. HA dissociate in water. We measure the pH of the obtained solution equal 3.7. So the degree of dissociation HA is, so the objective is to calculate alpha, the degree of conversion or the degree of dissociation, knowing the concentration and the pH. In the previous example, we calculate Ka knowing C and alpha. In this exercise, we want to calculate alpha knowing C and pH. So again, we have to write the equilibrium dissociation of HA in water, C0, 0, 0 at T equals 0, at T equilibrium C0, 1 minus alpha, C0 alpha, C0 alpha. The pH equals 3.7, and the pH equal minus log HCO plus at equilibrium. So pH equal minus log HCO plus, and HCO plus equal 10 to the power minus pH equal 10 minus 3.7. and this value 10 minus 3.7 is equal to C0 alpha. So C0 alpha equal 10 minus 3 times alpha equal the concentration of HCO plus at equilibrium 10 minus 3.7. So we calculate alpha equals 0.1995. So alpha is approximately equal 20%, but less than 20%. Again, this acid used is of weak behavior since alpha is less than 20%. The answer is B. Exercise 18. Calculate at 25 degrees the pH of nitrous acid solution HNO2 of pKa 3.2 at different concentrations. So the objective of this exercise is to know which formula of the weak acids formulas should be used according to the concentration in question. We'll start by part A. The concentration is 10 minus 1 and Ka equal 10 minus 3.2, so we have to compare C0 to Ka. C0 equal 10 minus 1, 100 Ka equal 100 times 10 minus 3.2 equals 0.063. So C0 is greater or equal 100 times Ka is valid, so the formula that should be used pH equal half pKa plus pC0. So pH equal half pKa minus half log C, and the value is equal to 2.1. In part B, the concentration is equal to 10 minus 3. And if you compare C0 to 100 Ka, C0 is not greater or equal 100 Ka, so the formula used in part A could not be used. We have to use to solve the second degree equation HCO plus square plus Ka HCO plus concentration minus Ka C0 equals 0. So we put Ka by its value and C0 by its value, and we find that HCO plus concentration at equilibrium equal 5.39 10 minus 4. pH equal minus log HCO plus in the solution, so pH equal 3.26. The objective of exercise 19 is the same as number 18. Calculate at 25 the pH of ammonia solution, which is basic, of concentration 10 minus 4 molar given pKa. Since we have a base, it's preferred to work on Kb and not on Ka. And Ka and Kb of the same couple are related according to Kw. So pKa plus pKb equal pKw equal 14. So pKb equal 14 minus 9.2 equal 4.8. We want to calculate the pH of weak base. We have three formulas according to the domain of validity of the concentration. So now we have to compare the initial concentration of the base ammonia with respect to Kb and not Ka. So comparing C0 and 100 Kb, we found that C0 is not greater or equal 100 Kb. So the formula POH equal half pKb plus pC0 could not be used, and we have to apply in this case the second degree equation. OH minus square plus KBOH minus KBC0 equals 0. Put KB and C0 in their values. So we obtain a solution of this quadratic equation. Concentration OH minus equals 3.27 times 10 to the power minus 5 molar. POH equal minus log OH minus in the solution. So POH equal 4.49. POH plus pH equal 14. We find the value of pH equal 14 minus 4.49. So equal 9.51. We pass to exercise 22. Consider a monochloroacetic acid solution of concentration 10 minus 3 molar. A dilution is carried to 150 of the initial concentration. So we did 50 times dilution. Knowing that pKa of the couples are given, which of the following statements are correct concerning the obtained solution? If we look to this acid, this is an acid weak of Ka 10 minus 2.9. The dilution factor F is equal C initial divided by C final equal V final divided by V initial, or in other words, C initial, V initial equals C final, V final. The factor of dilution equal initial concentration divided by the final concentration. So the factor of dilution equal 50. We did 50 times dilution. The concentration final after dilution equals C over 50 equal 210 minus 5 M. This is the concentration of the weak acid after dilution. So now, comparing the value of the concentration with the value of Ka, we found that C0 is it not greater or equal 100 Ka. That means the acid we used in this exercise is weak, but is not of weak behavior. So the dissociation cannot be neglected in this case, since it's not of weak behavior. So A is false. In part B, they asked to calculate the pH of the solution. In the previous slide, we found that C0 is not greater or equal 100 times Ka, so the formula pH equal half pKa plus PC0 could not be applied, and we have to solve the second degree equation, HCO plus Ka HCO plus minus KaC0 equals 0. Put Ka and C0 in their values. You will find HCO plus in the final solution equal 1.96 10 minus 5. pH of the final solution equal minus log HCO plus in solution, so equal 4.71. So B is incorrect. B is false. We pass to part C. The auto-ionization of water is not negligible. So he proposed that we did not neglect the auto-ionization of water. This is false. Since the auto-ionization is negligible, the concentration of HCO plus from the weak acid is equal to 1.96 10 minus 5 molar, which is greater at least 10 times than the HCO plus provided by the autoionization. So in this case, HCO plus in the solution is only equal to HCO plus from the dissociation of the weak acid, and the autoionization is neglected, so C is false. In part D, he proposed for the estimation of the pH, it's necessary to solve a second-degree equation. D is false. In this case, when we use the second-degree equation, this is not an estimation. This is the precise method. So D is false. In part E, the pH of the solution equal 4.71, and this is the value of pH we calculated, so E is true. The correct answer is only E. Exercise 30. Calculate the initial concentration of acetic acid to obtain a solution where the concentration at equilibrium is 3.5 10 - 4 molar and given Ka of acetic acid. Again, we have to write the dissociation of the weak acid in water at T equals 0. We have C 0 0, T equilibrium C minus X X X. The concentration of HCO plus at equilibrium is equal 3.5 10 - 4. So HCO plus equal acetate equal X equal this value. Ka equal the concentration of the products divided by the reactant at equilibrium implies acetic acid at equilibrium equal acetate at equilibrium times HCO plus at equilibrium divided by Ka. So the concentration of acetic acid at equilibrium equal 3.5 10 - 4 times 3.5 10 - 4 divided by Ka, which is equal 1.8 10 - 5. So the concentration of acetic acid at equilibrium equals 6.805 10 - 3 molar. And we know that the concentration of acetic acid at equilibrium is equal to the initial concentration of acetic acid minus X. So the concentration C is equal to the concentration of acetic acid at equilibrium plus X, or the concentration of HCO plus at equilibrium. So it's equal to 7.155 10 - 3 molar. The correct answer is C.